This is the basic circuit of power line carrier communication. You can see here is the power station. This is my load. This is my source resistance, that is the source resistance of power station, whatever it is. So now what we do is we superimpose 50 hertz component of the power line with a 5 kilohertz signal. Now to do this, we require two analog components here, the coupling transformer and the capacitor necessary for coupling. Like we are connecting two sources in parallel, so we have to take care that they should not like short each other, or circulating current should not be there. So capacitor takes care of that. You can see the output I have connected to oscilloscope. You can see the component is 50 hertz and a 5 kilohertz component can be seen. Yeah, this is the power 5 kilohertz component. This is 50 hertz. If we analyze this, the Fourier analysis, and you'll get something like this. So here we have this horizontal axis is frequency, vertical axis is the voltage magnitude. So you can see here approximately at 50 hertz you are getting a large component, and also at 5 kilohertz you are getting a large component. So the signal consists of two components, 50 hertz and 5 kilohertz. 50 hertz is power component and 5 kilohertz is the communication component. And you can see here the 5 kilohertz is significantly higher. That's why the waveform is so distorted, as we saw. So we can attenuate a 5 kilohertz component by manipulating the capacitor value. Now this capacitor value can be manipulated. Suppose if I write it 0.5, 0.1 micro, then we'll get a attenuated wave. So if I just play it, yeah, the component has reduced. So if we analyze it now, then yeah, the 5 kilohertz component is a little attenuated, so we can manipulate the capacitor value to get this. So that's the basic circuit. So we have the power system. Now what is there in the power system? This, the first part is generation, and then we transmit, then there's distribution. Now there are different voltage levels here. As you can see, this is 132 kV, 11 kV, and our home supply is at 230 kV. Now we will be implementing two concepts basically. The very first concept is at the distribution level. So at the distribution level, what we'll have is the electricity bill measuring system. So at every house we'll have our own modem, TX and RX. RX is for address receiving and matching and all that. TX is for sending the meter data, that is the energy meter data and the power quality meter data. Both these meter will be integrated in our module, so you can use TISs for both of them. Now this data will be sent to the nearest electricity billing center, and this link is via 230 volt. Electricity billing center will have a control unit which will monitor the power quality and whatever it want to monitor. We can request the control unit anytime what is my bill currently via some, like by using my own modem at my house. So like many things can be done here. The second concept that we can implement is the load dispatch center. What happens is, for every power station we have a PCR, that is power station control room, which sends the generation, that is current generation of the power station, of my power station, to the load dispatch center, which is located like maybe 1,000 kilometers away. So Maharashtra has two load centers. So like this, we can use a PLCC, TX and RX for that communication. We can send the power station generation data to the load dispatch center. Load dispatch center will get the data in real time. It can monitor the power generation. There's no need of any kind of telephone calls. So this is the real-time monitoring system. The second thing. Now when we are implementing, there's one thing we need to take care of. There are transformers in the power system everywhere to step up and step down. So transformer is basically a pass band filter. So I'll take you to new circuit. Yeah, this is the equivalent circuit of the transformer. So this is ideal transformer and all equivalent circuit. You can see inductances, resistances. So this creates a pass band, which you can see. So this is the pass band you can see. Now it passes the frequency up to only 10 kilohertz something. Here it shows 10 kilohertz because I have chosen the parameters like that. In real life, the transformers, they allow 400 kilohertz frequency, up to 400 kilohertz. After that they attenuated badly, right? And we can't use those frequencies because our signal will be too attenuated to get detected. So here we have to bypass maybe the transformer. So what we can do here is we'll short the neutral. As you can see, the ground will be shorted, and we can have a bypass system like this, PLCC RX and TX. What will happen here is, if you have a 50 megahertz component at this place, you won't get the component here, right? Because transformer will block it. Now to get the component here also, what we'll do is, this upper RX modem will detect that 50 megahertz component, and this TX modem cascaded with it will generate that 50 megahertz in the next line. So as you can see, my 50 megahertz will come here. From here it will go to RX, it will again go here. Now you may ask if we can directly couple it so that the component can be introduced, but no, we can't couple it directly because it will be like shorting the transformer, and there's no use of transformer. So we have to have a digital isolation. So this thing you're watching between PLCC RX and PLCC TX here is the isolation we are providing. So we are not shorting transformer, so no one will argue with this. I explained for 50 megahertz from this side. From if it comes from this side, then the same thing should be there. So these system we have to implement on every bad transformer in the power system. Bad as in which has less band pass. So this is one thing which we should look into. Well, that's it.